Okay, so the next one is exercise 67, and this is about the Verhoeven check digit scheme. Now the solution to this one is already there in the part titled answers at the end of the text. Now if you go and see the solution, you will see that almost the full solution is there, except this one. This computational task has been left to us by the author, and this is something that we have to check or verify case by case. Whenever a and b are distinct digits, we have to see that these two quantities are not the same, they are distinct. So this I leave to you. The rest of the solution is there and it's easy to understand. Still, if you have some doubts, you let me know in the comments below. Instead, let's now see the next one, and in this one we are given a number, and for this we have to use Verhoeven's check digit scheme to append this number with a check digit. So we are now going to calculate the check digit. So let's see the solution. Let k be the check digit. Then according to our scheme, sigma of 4 star sigma of 5, sorry, it's not sigma of 5 but sigma square of 5 star sigma cube of 7 star sigma to the power 4 of 2 star sigma to the power 5 of 3 star sigma to the power 6 of our check digit is equal to 0, where sigma is this permutation. I'd better write it in the next line. Zero 1 5 8 9 4 2 7 times, it's this cycle times 3 6, which the cycles together involve all the digits in the decimal number system, and where star is of course the binary operation in the dihedral group D5, we already understand these things, where these digits actually are interpreting the elements of D5 according to a scheme, where the first few elements are rotation and the rest of them are reflection. You know this thing. Okay, so now using this equation we have to calculate k. Now the above equation becomes what we now have to put these values. Already tables are given in the text. Using the tables, you can quickly just read off these values from the table, and then you will get this. 2 star 9 star 5 star 5 star 6 star sigma to the power 6 of k equal to 0. And this ultimately turns out to be this part, except sigma to the power 6k turns out to be 0. And the way we are interpreting these digits as the elements of D5, 0 represents the identity element in D5. So this, and this implies that k has to be equal to 5. In the table where you have the values of these first few powers of sigma, you look at the row corresponding to sigma to the power 6, you will see that in that row sigma to the power 6 of 5 is equal to 0, and 5 is the only element, of course, whose sigma to the power 6 image is 0. So that's why k is equal to 5. So this is the check digit. Now I want you to go to the text and actually see that this calculation is true, because this answer I could not find anywhere. So maybe I have made a mistake. So you please verify it and let me know if I made any sort of mistake, or even if this is true, still you let me know. Now let's see the next one. Prove that every element of Sn where n is greater than 1 can be written as a product of elements of the form 1, k. In the text, of course, it's given as 1k, but because I have decided to use commas to separate the symbols in order to avoid any confusion, so I am writing it as 1, k. That is, we have to prove that in the symmetric group Sn, every element can be written as a product of elements of this form. Now note that we already know that every element in Sn is a product of 2 cycles or transpositions, and this is a particular type of 2 cycle. So it's enough to show that any 2 cycle can itself be written as a product of elements of this form. Then automatically every element will be so expressible and our job will be done. And in the solution, we are going to recall that this fact that I just said right now about permutations is in fact the claim of theorem 5.4, by theorem 5.4 every element of Sn where n is greater than 1 can be written as a product of two cycles, and any two cycle in Sn is expressible like this. And perhaps I should also say here we are assuming that A and B are both different from 1. And in fact that is the solution. Why? You see, why do we need both A and B to be different from 1? That is because if one of them is 1, see, we have already said a 2 cycle. So because we are saying this is a 2 cycle, A and B are different. Whatever they are different. So if one of them is 1, the other one will not be 1. But if one of them is 1, then already this 2 cycle is of this form and we need not do anything else. However, if both of them are different from 1, then this 2 cycle can be written like as this product. Now let us actually verify if it is true. Our calculation starts from this side because we are writing the input of a function to the right of the function symbol. So this is a product which after all is a function, a permutation, and the input lies to this side. So what does this product do to 1, say? It takes first this one takes 1 to A, then next that A is unchanged by this middle one, and then that A is sent back to 1. So this product maps 1 to 1 itself. Okay, so 1 does not appear here, fine. A is sent to 1 by this one first, and then 1 is sent to B by this middle one, and that B is unchanged by this because B does not appear here. Why is B not here? See, B is not equal to 1. Also, this being a 2 cycle forces us to have B different from A. So that is why B is neither 1 nor A. So this B is then unchanged by this one. So that means A is mapped to B. A is mapped to B. Okay, then what about B? The first one does not change B. The second one takes B to 1, and the third one takes that one to A. So B gets mapped onto A, B gets mapped onto A. And if other symbols are also available in Sn, I mean in the underlying set whose permutations we are considering in Sn, if other symbols are available, then none of them will be changed by this product, because simply none of them appears here. Okay, so they are kept fixed by this product. So that is why this product is equal to economy, and we are done. And let me just end things here itself, because after this we have a ring theory video also. So see you in that video.